At the edge of the cosmos, there exists an enigma that challenges basic notions of temperature. There is a thermal boundary that separates our reality from the unimaginable. That minimum temperature is known as absolute zero and is impossible to cross. The thermal barrier is set at -273.15 degrees Celsius. This phenomenon is not a scientific curiosity, but may be the key to the most fundamental secrets of the cosmos. From the most intimate nature of matter to the very structure of the universe and its beginnings. Get ready for a great journey to the very heart of matter, where you will discover that temperature is much more than a simple measurement. The lowest temperature that we have detected in the universe is -272 degrees Celsius and was detected in the Boomerang Nebula, thanks to a sub-millimeter wave telescope, which when pointed towards it detected this area in the constellation of Centaurus, about 5,000 light-years. Although this is only the beginning, since we know that theoretically the temperature can still be lower. The current world record for minimum temperature, which we have achieved through matter wave lenses of rubidium condensates, reaching 38 picokelvin, is almost absolute zero. But why can't we reach absolute zero? And what would happen to matter if we achieved it? First of all, I will tell you that temperature is the degree of atomic and molecular movement that matter has. The more the particles move, the higher the temperature. Tell me how you move, and I'll tell you what temperature you are at. This movement is everywhere in the universe, from gases to liquids. Living beings can perceive the temperature of things, even air and liquids. The average temperature on Earth is about 14 degrees Celsius, and the lowest recorded on our planet is -89.2 degrees Celsius in Antarctica, and the highest is 56.7 degrees Celsius in Death Valley, in California. You have surely noticed that the temperature ranges in which life is possible are closer to absolute zero than other high temperatures in the universe. For example, our Sun reaches about 5,600 degrees Celsius on its surface, and in its core it can reach 15 million degrees Celsius. Matter is transformed at high temperatures, becoming plasma and gas. Like the stars, or at the time of the Big Bang, where everything was concentrated in a state of plasma at 1,000,000,000 kelvins, and the atoms of matter could not be formed. When the universe cooled, the particles calmed their frenetic movement and were able to unite, forming atoms and therefore the elements, up to the solid matter that we know. Temperature changes the appearance of matter. As the temperature of matter decreases, the particles that compose it tend to lose kinetic energy, leading to changes in their behavior and structure. For example, when liquid water turns into ice. Today, the universe has cooled to 27,042 degrees Celsius. Based on measurements of cosmic microwave background radiation, this cosmic X-ray provides crucial clues about the thermal evolution of the universe over time. According to models of the expansion of the universe, they predict that the average temperature will decrease over time. This is due to the average energy density in space. It has nothing to do with the temperature at which the particles move. If we could reach absolute zero, any atomic activity would stop and any movement would be reduced to zero. We know this now, but centuries ago it was not so clear. The first person to think about a lower possible temperature was Guillaume Amontons, a French scientist-inventor, born on August 31, 1663, and his contributions to the fields of physics and engineering were significant, being known for his discoveries in thermodynamics and fluid mechanics. One day when he was working on improving his thermometer, in that thermometer the temperature was measured by the height to which a column of mercury rose due to the heat of the air. Amontons, so he wondered if there was a limit to how cold something could be, and if there was, where the starting point would be. He assumed that the lowest point should be when the volume of air in the thermometer was reduced to nothing. At that time it was thought to be around -240 degrees Celsius. These experiments contributed to further exploring these ideas. Thanks to the works of Gabriel Fahrenheit, Anders Celsius, and Lord Kelvin, he established the notion of absolute temperature, and absolute zero was defined as the lowest temperature theoretically possible, at -273.15 degrees Celsius. Thanks to the fundamental principles of thermodynamics, Kelvin established its scale without negative values, since it only reflects the minimum thermal energy of a physical system. You will surely be familiar with the Fahrenheit or Celsius scales that we usually use in our daily lives, and that has nothing to do with the definitions of the Kelvin scale, which is more used in physics, chemistry, and astronomy. If we want to understand why it is impossible to reach absolute zero, we have to explain some basic concepts of thermodynamics. If temperature is the energy of particles in continuous motion, absolute zero is like the lowest limit, where the particles are so cold that they practically stop moving. In thermodynamics, we study how energy moves between different forms and systems. When we get closer to absolute zero, things get a little strange. Thermodynamics tells us that when reaching absolute zero, the systems cannot transfer heat normally. This relates to something called entropy, which is like a measure of the disorder or uncontrolled energy of a system. When we are close to absolute zero, the entropy becomes very low, as if everything were calm. If we want to cool something, we must transfer that heat to the environment, and there comes a time when, close to absolute zero, it will take infinite work to transfer some heat to the environment. This is the third principle of thermodynamics, which tells us that it is impossible to reach absolute zero in a finite number of steps. In other words, reaching super low temperatures is very difficult and impossible and takes a lot of time and energy. So in summary, absolute zero and thermodynamics teach us that there is a super low limit in the cold where things get very strange and difficult. Absolute zero is a real measurement, and we have been trying to reach it for decades but without success. It is like the speed of light. You can get close to it, but not reach it, because if you did, something dangerous would happen. Now suppose we reached absolute zero, what would happen then? We know that as you approach absolute zero, the kinetic energy of the particles is reduced to a minimum. At absolute zero, all particles are expected to reach a state of absolute rest, meaning that they stop vibrating or moving. Matter would be in its most ordered and static state possible. Entropy would reduce to zero, and quantum mechanics would become dominant. We have been able to see this in Bose-Einstein condensates, where the particles occupy the same quantum state. The existence of this state of matter was already predicted by Albert Einstein in 1925, and was based on the work of the physicist Bose. This was confirmed in 1995 in the experiments of Eric Cornell and Carl Wieman, who obtained this special substance using a gas of rubidium atoms, down to almost minus 273.15 degrees Celsius. On the other hand, reaching the minimum temperature would violate the uncertainty principle, which tells us that we cannot simultaneously precisely know the position and momentum of a particle. Quantum particles, such as electrons and photons, exhibit both particle and wave properties, and there is no telling where that particle will appear in the associated wave. This in theory, but in practice things would get creepier. In 1802, Joseph Louis Gay-Lussac, who knew a lot about substances and how they behave, discovered something very interesting about gases. If you have a gas and you keep the pressure constant, as if you were keeping it in a closed box, it turns out that if you raise the temperature, the gas expands. But there is something more curious. For every degree that the temperature rises in degrees Celsius, the volume of the gas increases by 1 part in 273 of its volume at 0 degrees Celsius. This rule is pretty neat and works for any type of gas, no matter what it is made of. Now comes the most interesting part. When you bring the gas to a temperature of minus 273.15 degrees Celsius, something strange should happen. According to the rule, the volume of the gas should be 0. In other words, the gas would simply disappear. Reaching absolute zero is the same as reaching or exceeding the speed of light, or even eliminating the 0-point energy, represent unrealizable goals that, if achieved hypothetically, could make information disappear from the universe, or change our reality. It is important to note that physical laws will never allow this, since strange and irreversible situations would occur. But even in our experiments, we are achieving surprising things. Near absolute zero, we are seeing really strange phenomena. At very low temperatures, some materials exhibit the phenomenon of superconductivity, where resistance drops to 0. This allows the conduction of electrical current without loss of energy. Superfluidity. This is the same as superconductivity but for fluids. Some liquids can exhibit superfluidity at very low temperatures, such as helium-2. In a superfluid state, the fluid flows without friction and can ride up the walls of containers. There is no container capable of containing it. We have achieved a new state of matter, the so-called Bose-Einstein condensate. At temperatures close to absolute zero, certain gases can form a Bose-Einstein condensate, a state of matter in which the particles occupy the same quantum state, and they behave as a single quantum entity. The best thing is that by almost completely stopping atomic activity, we can observe quantum mechanical phenomena, such as individual particles, much better. You can see the great wonder of quantum mechanics through microscopes. This has led us to the development of technologies such as superconducting magnets for nuclear magnetic resonance, cooling lasers, and high-precision atomic clocks. These discoveries take us to the very nature of the universe with which we can obtain new materials and surprising discoveries. Absolute zero is not just an extreme temperature. It is a threshold that opens a door to dimensions beyond our understanding.